Hi guys, I wanted to make sure that we finished up the structure of the Earth notes. First period and second period classes, we have done the first couple slides, so you can just go ahead and fast forward until you get to the information that you need. Fifth period, we are going to start fresh at the beginning. I want to first remind you of our content standards, and that those are that we need to understand how scientists know about the interior structure of the Earth, and that the Earth has layers and what those layers are. We've already done the notes where we've talked about the main layers of the Earth, the crust, mantle, inner and outer core. So what I really want to talk about today is how do we know about the inner structure of the Earth? And as you can see, there are two main reasons, or I should say two pieces of evidence that we have that tells us about the interior structure of the Earth. The first piece of evidence is that we know that the Earth is not solid because seismic waves slow down when they reach the outer core. And if you remember the lab that we did, we first used model data of seismic waves traveling through a homogeneous Earth, meaning the material is the same from the crust all the way to the core, and seismic waves behaved a certain way. Well, when we graphed the data from actual seismic stations, we found that seismic waves do not behave that way, and that they slow down once they reach a certain point. Okay, and we now know that it is because once the seismic waves reach the outer core, they slow down. The second piece of evidence is that we know that the Earth has layers because of the direction that seismic waves are reflected and refracted inside the Earth. And we're kind of talking about shadow zone here. If you look at the picture right over here, okay, or let's start at the bottom. This picture shows seismic waves, how they would travel in all directions away from the earthquake if the Earth were homogeneous. Okay, they're traveling all directions same time. Here in the second picture, okay, you'll notice that as waves travel, okay, they reach this area where they no longer travel through the Earth because the outer core is blocking them. In the top picture here, this shows you how the P waves get reflected and refracted through the inner and outer core and where they show up on the other side of the Earth. Okay, so we're going to go on to the next slide. And this slide is telling us how do we know what the Earth is made of. Okay, well, we know what the Earth is made of from a couple of pieces of evidence. The first one we've talked about, and that is core samples. We have actually drilled into the crust, and we can pull up those materials and analyze those and determine what type of minerals are present. We do have a few samples of the mantle, and I know that sounds a little strange because the mantle is so deep, and we know that we have not come close to drilling into it. But please remember that when volcanoes erupt, sorry about that, and you're gonna have to bear with me, this is my first time trying this, so again, please be patient with me if I make a few mistakes. When volcanoes erupt, they bring up parts of the mantle, and so when that hot magma makes its way to the surface and becomes lava, and then we can analyze it, and that gives us a clue as to what's in the mantle. The third piece of evidence is the Earth's magnetism. Okay, and we believe that the Earth has magnetism because of the fact that the inner and outer core are made of iron, and we know that iron is magnetic. The last piece of evidence would be meteorites. And if you remember from the video, we saw meteorites, when we analyze the meteorites that have made their way to Earth, okay, we can tell what elements are present in those meteorites. Okay, and we also see many of those same things in the Earth. Okay, next, what is the inner core made of? Well, the inner core is solid and is made of iron and nickel. And there are three pieces of evidence that we have that tells us this. One, again, is the composition of meteorites. Okay, they are mostly made of metal, or I should say the metal iron. Okay, and there are a couple different kinds of meteorites actually. There's iron meteorites, there's stony meteorites, and then there's iron stony, which is kind of a mix of the two. But basically, we believe that, what meteorites are made of is the materials that the Earth first formed from. The inner core is also, again, we talked about the fact that it gives the Earth its magnetic field. Scientists believe that the magnetism of the Earth is caused from the liquid iron and nickel in the outer core. There's convection currents that occur in the outer core, causing hot material to rise, cooler material to sink, and this kind of creates this whirlpool, which, as that metal moves around, it creates electric currents, which in turn gives us the magnetic field of the Earth. The third piece of evidence we have is how seismic waves behave. The seismic wave patterns that we see. And if you look at the picture on the Earth, again, this part represents section A, and that is where all of seismic waves will reach elsewhere on the Earth. Part B, this is the shadow zone where no seismic waves reach the other side of the Earth. And then part C, those are P waves that have been reflected and refracted, or not reflected, but just refracted through the outer core, the inner core, back out the outer core, and then through the mantle and crust. So again, we can look in the laboratory, we can see how seismic waves behave going through certain materials, so that way when we see that same pattern on the Earth, we know what is happening, and that gives us this evidence that the inner core is made of iron and nickel. So we're going to go on to the outer core, and this is liquid iron and nickel. And again, we know this because S waves, will not travel through this layer. They are shear waves, they do not travel through liquid. The fact that the S waves have such a huge shadow zone on the Earth tells us, that the the outer core is blocking those waves from reaching the other side of the Earth. So let's go ahead and move on to the mantle. The mantle is made up of the elements silicon, oxygen, and magnesium are the most abundant materials in the mantle. The evidence we have are rare mantle rocks from areas of mountain building and mantle plumes. So some places on Earth, when mountains have been built, they have been compressed and made folds, and then a lot of times you have fractures and faults, and some of those rocks are then brought to the surface and exposed. And this gives us the chance to look at rocks that are deeply buried and perhaps are, from the mantle. Mantle plumes. Plumes are hot rock that have made their way to the surface, or sometimes they're deep within the Earth. We have these areas that have heat and the material is melted, and then through, other types of either mountain building, folding, faulting, those are brought to the surface, and we have the ability to analyze them. So one other very important fact about the mantle, and that is that it is the largest layer and that it makes up 80% of the Earth's volume. And if you recall, when we created our model, when you guys used the compass and made your layers, the mantle was the largest in our drawing as well. So let's talk about the mantle. And the mantle is split up into 3 different parts. The first part is the upper portion. It is rigid and it's part of the lithosphere. If you look at the picture here, this part represents the lithosphere, and it is made up of the oceanic and continental crust and the upper part of the mantle. So again, this part of the mantle, the upper mantle and the crust, makes up the lithosphere. And the lithosphere, lithos means rock, and that is what, and we're going to learn in the future about the fact that we have tectonic plates, and the lithosphere is broken up into these tectonic plates, but that's, we'll talk about that in the next few weeks. Second part of the mantle, and this is a very important part, it is the portion with plasticity, and it is called the asthenosphere. And what I mean by plasticity is, in a way, it sort of acts like silly putty. Okay, if you hold silly putty in your hand, you know that it's a solid, but you can press it and move it so that it is flexible. And the rock in the asthenosphere has this ability to what we call flow. And we're going to learn next about convection, and convection is how that rock flows. And that is, hot things rise, cool things sink, and in turn it creates the cycle in which it does it again. But again, we will talk about that next week. The third part is this part here is the asthenosphere. Okay, and then below that is the lower mantle. It is called the mesosphere, and it is also solid. Okay, and just, close up here of, again, the lithosphere is the upper part of the mantle, and the crust, both continental and oceanic crusts. The middle part is the asthenosphere, and again, this is so important because this layer, or this part of the mantle, has the ability to flow, or it's flexible, it can move. Then, of course, the lower mantle is, again, solid. Okay, characteristics of the crust. This is important to us because this is where we live. It is the thinnest layer, and if you recall from your drawing, you definitely knew that. It was barely 1 millimeter thick, and it was very hard to draw. It is the least dense layer, and we know that because we can analyze it. It is composed mostly of silicon and oxygen. The crust also has both continental and oceanic rocks. So at the bottom of the ocean and under the biggest mountains. It contains igneous, metamorphic, and sedimentary rocks. If you recall, igneous rocks, these come from volcanoes. Metamorphic, okay, morph means to change. These rocks have changed over time. And sedimentary rocks are made of sediment. Things like sand particles, rocks, pre-existing pieces of other rocks. And of course, it would make sense that the crust is thickest under the mountains, thinnest under the oceans. And I have to hurry here because I only have 15 minutes, so I'm looking and I have a couple more slides. Again, this is a great picture because it talks about, okay, if you look on the left side, these are layers that are based on chemical properties. On the right side here, layers based on physical properties. Okay, and this is, again, we have the lithosphere up top, we have the asthenosphere, the mesosphere, outer core, inner core. Okay, here if we look at their chemical properties and what they're made of, okay, we have the core, we're including both inner and outer here, the mantle, which is made of silicates, and the crust silicates. All right, and of course, the important part of this is, how did the Earth become layered? Okay, now that we have this evidence that it is, how did it become that way? And basically, we call this planetary differentiation, and it's the process in which more dense materials of a planet sink to the center and the less dense materials rise to the surface. And so how does this occur? Well, if you recall in the film, the first step here is mineral grains clumping together. Now we add radioactive material and then more bombardment, and we have heat. So if you look in the core here, it's turning red, it's starting to melt. Okay, in this picture right here, this is where, the Earth is formed, and it is in this process of melting due to radioactive elements and the bombardment of materials. And then over time, as it cools, the layers differentiate. The heavy, dense stuff goes to the center, and the least dense materials on the surface. Okay, and something else that we needed to do, and that was take a look at other planets. Okay, this shows Mercury. You see Mercury has a lot more iron in its, its core would be bigger than the Earth, rock on the outside. And I don't know if you remember from the one PowerPoint, but it talked about, this kind of proves that there was less water available to Mercury because there's more iron in the core. Remember, there's not much for it to bond with out here and make lighter elements. So all of that sunk to the center, which I found very interesting. So I just want to reiterate, why we're doing this is to explain how scientists know about the interior of the Earth.